Hello and welcome to the Ohm's Law Lab. Ohm's Law is one of the fundamental relationships that we find in electricity and electronics. It's used everywhere. Interestingly, it's not always true, but it's true in so many cases that it's very important that we cover it. The relationship simply states that if you apply a potential difference or electromotive force across a resistor and measure the current, if you multiply the current times the resistance, you will get the electric potential. It also says that if you vary the electric potential and watch what happens with the current, that you will get a straight line relationship between the electric potential and the current, and the slope of that line is the resistance. That is how we are going to measure the resistance of the two devices that we are going to study today. So before we dive into the analysis, which is not difficult, let's drop out here and go to the lab and see exactly how the voltage was varied and the current was measured. This is the apparatus that we use to acquire the data for the Ohm's Law Lab. On the left, in gray, we have a voltmeter accurate to 1/100th of a volt. Near the center, in yellow, we have a milliammeter, right now reading 1.00 milliamperes, thousandths of an ampere. And at right, we have a small gray power supply which can be adjusted from about 5 volts up to about 19 volts. Now the current comes out of the power supply on a silver cable, comes around and connects to the positive lead of the milliammeter and goes in. Then it comes out of the milliammeter and comes up to our resistor, which is the little ceramic block that you see there. This particular resistor is 5.01 K ohms. The current then goes from the other end of the resistor to the black connector on the end of the silver cable and returns back to the power supply. Connected across the resistor are the positive, red, and black negative leads of the voltmeter. To acquire the data, we change the voltage from the power supply from 5 volts up to about 19 volts, and at a variety of different voltages, we read the corresponding current on the milliammeter. Here, we're at about 5 volts, and we're reading 1.00 milliamperes. We can raise the voltage to perhaps 7.5 volts. It takes a while to settle down. That will do. We have 7.43 volts, 1.49 milliamperes. We increase the voltage in nice steps, working our way up to a maximum of about 17.5 volts. Again, it takes a while for the voltage to stabilize. So here we are at 17.46 volts and 3.49 milliamperes. Then we change the resistor from a 5.01 K resistor to a 2.04 K resistor. We'll take time out to do that. Here, everything is exactly the same as it was before, except we have changed the resistor to a 2.04 K resistor. The voltage is about the same, but notice how much larger the current is. It's over 8 milliamps now. We do the same process for this resistor. We start at about 5 volts, and here we have 4.94 volts DC and a current of 2.43 milliamps. Notice it's much larger than it was before. I think before when we started it was 1 milliamp. We gradually increase the voltage in nice even steps, 7.5, 10, 12.5, and so forth. Here we are at about 10 volts. So we have about 10 volts and 4.96 milliamps. And again, we work our way up to about 17.5 volts, writing the data down for each data point. That'll do 17.39 volts and 8.52 milliamperes. Next, we will talk about how we are going to analyze this data. Now that we can see how the data was acquired, let's go take a look at a circuit diagram of that setup. What we had was a power supply, which is drawn like this. I draw a power supply as a battery symbol with an arrow through it because you can vary the potential difference. Technically, we talk about potential difference, but casually it's often called the voltage. All right? We passed the current through a meter to measure the current in milliamperes. We then allowed that to go through the resistor, R in this case, and we used two resistors. First we used a 5.01 k ohm resistor, and then we repeated the whole experiment with a 2.04 k ohm resistor. Then the current comes back to the power supply. Connected across the resistor is a very accurate voltmeter. So we can simultaneously measure the voltage across the resistor and the current flowing through the resistor. Now, that data is tabulated in the two tables in the student report sheet. The data analysis requires you to make two graphs, but on a single piece of graph paper. And that's going to be the hard part of this lab for some of you. There's a file attached to the email which contains an image of graph paper. If you have access to a printer, all you have to do is print that out and you're ready to go. You will be turning in one sheet of graph paper, but it will have, as you can see here, two graphs on it. If you cannot print out that PDF file, then you have to either get some graph paper from someplace, or you're going to have to make your own. If you must make your own, you can use notebook paper. Don't try and you got to start with at least notebook paper, which is a set of parallel lines. Then you can draw vertically spaced, equally spaced lines along that to make the graph paper. But if you don't get those vertical lines perfectly parallel to each other and at perfect right angles to all of the horizontal lines, it's not going to work. Also, if you draw those vertical lines, they must be equally spaced. I urge you to try and find access to a printer where you can simply print out the PDF file, which contains this, okay? So you can make the graph paper yourself, but you've got to be sure that the spacings are equal, that the lines are parallel, and so forth. One thing that is a little bit forgiving is that if you make your own graph paper, when you draw the vertical lines, they don't have to have exactly the same spacing as the horizontal lines. You can have little rectangles. But they must be equally spaced. Otherwise, when you calculate your slope and plot your points, it won't work. Really try to get access to a printer and print this out, or try and get some graph paper from some place, okay? They often have graph paper at Walmart or at the drugstore or whatever. I know you got to buy a whole pack of graph paper, but what the heck, okay? Alright, so what do? Well, first of all, if you use this graph paper, you got it made because the data that we have perfectly fits this graph paper. It just turned out that it was a very lucky choice of data and graph paper. You want to make your graph, this way. Long-wise is horizontal. Short-wise is vertical. Okay? You'll see that there are exactly 10 of the heavier lines going horizontally. Since the data goes up to about 10 milliamps, if you use a scale across the bottom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 milliamps, where these are the heavier lines and the finer lines are in between, that's absolutely perfect. Also, on the vertical axis, if you use 2.5, 5, 7.5, 10, 12.5, 15, 17.5, 20, and then the fine boxes are in between, this was just absolutely perfect for the data that we have. So put your graph this way, and across here you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and over here you have 2.5, 5, 7.5, 10, 12.5, 15, 17.5, 20. It doesn't get much better than that. You do the first resistor, which is, we're calling it R1. It is 5.01 K ohms, not 5.10. That's a common mistake for people to make. It's almost exactly 5,000 ohms, 5.01 K ohms. You plot those data points and you should get a graph that is approximately this first one, okay, this first one. Because when you get to 17.5 volts, you only have about 3 3/4 or so milliamperes of current. You could also plot R2, which is 2.04 K ohms, not 2.40, 2.04. 3 significant figures. These are very close to 5 and 2 K ohms. Plot both graphs. Don't forget a title on the graph. Don't forget to label your horizontal and vertical axes. Don't forget to put the units that you're using. We're using volts for the EMF. We're using thousandths of an ampere, milliamps, for the current going across here. You plot your data points, and then you draw, as we've done several times now in the past year, the best fit line. If you do this correctly, the data is extremely accurate. It should be almost a perfect straight line. The data points should almost form a perfect straight line with very little scatter. If you have a data point that doesn't look like it's right, double check it. You may have plotted it wrong. The data is very, very good. Once you have them both plotted, you then want to find the slope of these lines, because the slope of the line is the resistance. Okay? So if we make a plot of E versus I, the slope is going to be R. In your sample calculations, you're going to show all of your calculations. You're going to have 2 complete sets of sample calculations. One for the 5.01 K resistor, another complete set for the 2.04 K resistor. For each resistor, you must do the following. You choose 2 points on the line that you drew that are not data points. Thou shalt not use data points to calculate the slope of your best fit line. You use points on that line, and you choose the points so that at least the vertical or horizontal coordinate lies on one of the grid lines. You may not be able to find it where they hit on a cross, but you can always find a point for your slope determination that is on a vertical or horizontal line, and then you have to estimate the value of the other coordinate, but do a good job estimating it. You mark those with an X on the graph. I have not done that for this one. This one will also have a set of slope points and a set of and so on. I haven't done it because it clutters the graph. I've only done it for this one so we can see it. You label the horizontal coordinate, comma, vertical coordinate. And yes, these points have units. This is in volts, this is in milliamps. I guarantee you I will be looking for that when I do the grading. I will look to see that your slope points have units on them. You do not need to put the coordinates of all the other points, just the 2 points that you're going to use to determine your slope. Once you have that, you come over here, and for each resistor you can divide the sample calculations area right down the middle and use the left half for one resistor, the right half for the other resistor. The rise is the difference between the right voltage value and the left voltage value. That's this distance, the rise. The run is the difference between the right current and the left current. That's this distance. The rise over the run then gives you the slope. Now, the units of rise are in volts. The units of run are in milliamperes. The slope is the resistance determined experimentally. It is the rise divided by the run. That will have units of volts per milliampere. But a volt per milliampere is the same thing as a K ohm, 1,000 ohms. A volt per milliamp is a K ohm, and so you can write this slope directly without any units conversion as K ohms. That is your experimentally determined value for that particular resistor. You can then compare it to the known value by subtracting the known value from your value and dividing by the known value and multiplying by 100%. This should be quite small. It's perfectly fine if this is negative. You may get a negative % deviation. It just means that your experimentally determined value came out to be lower than the standard value. You can keep, by the way, 3 significant figures through all of these calculations, even though the voltages are 4 significant figures. And in truth be told, the voltmeter used can give 6 significant figures. I rounded it to 4 significant figures. Your final answer for the resistance is going to be at most 3 significant figures because of the limitation on the measurement of the current. So in the end, your final deviation between the measured value and the actual value should be quite low. It's a very good experiment. Also, the fact that you do get a straight line means that these devices do in fact obey Ohm's law. Classic example of a device that does not obey Ohm's law is an incandescent light bulb. If you took a small, old style, not an LED, flashlight bulb, the type that actually has a filament in it, you would find that you would get a curved line when you did this, meaning that the resistance was increasing as you ran more and more current through the bulb. It's not a constant resistor. It doesn't obey Ohm's law for a good reason. The temperature inside that tiny light bulb changes from room temperature to thousands of degrees when you get it up to full brightness. And because the temperature change is so great, the result is the resistance of the device changes. It actually turns out for most materials, if you allow them to undergo a significant temperature change, it will not obey Ohm's law and the resistance will be different at different currents. But as long as you don't let the temperature change too much, and we're not doing that here, you get excellent agreement with Ohm's law. Okay, it's been wonderful working with you at a distance, but I'll tell you, it sure will be nice when we go back to having a real classroom and a real lab. I really like having students around. I like to look over your shoulders. I like to see what you're doing. I like to help you out. And working in this fashion, as we must, there's nothing we can do about it. Take care, and we'll see you later. Bye-bye.